Presentation, I want to say a few things about syntax and semantics, how to give it for a logical system. Now, this is just an overview of an overview of an overview, realistically speaking. I strongly recommend that you take a course on mathematical logic to understand how this works in a real system. Although we will give a syntax and semantics of a real system, it's just a very rudimentary system, but nevertheless, it's a very powerful system. So let's see what we need to do to provide a syntax and semantics. The syntax typically specifies how to form well-formed formula WOFs in the system. It also, by the nature of its specification, enables us to determine whether a given formula is well-formed or not. The semantics tells us how one can systematically determine the truth value of a well-formed formula. If we have a syntax of a proof system or a proof system in general, it will also tell us how to give proper proofs. A semantics will also tell us whether a proof is correct or not. However, in this presentation, we will only focus on the syntax and semantics of well-formed formulae. So what we will do is, as I mentioned, we will give the syntax and semantics of all, which is a fairly powerful logical system. It only has universal quantifiers and predicates, actually nouns to be specific. Technically, the only predicate is R. X is Y, R, RB. So it will be sufficient to understand why we need to give a syntax and semantics. And so this approach and some of the ideas and examples are inspired and given by Larry Moss, a friend of mine, a logician at Indiana University, who is one of the leading experts in natural logic. So you have seen his video on natural logic already. So what sort of reasoning do we want to capture? Again, remember, logicians study valid reasoning. And so there are these things called syllogisms that are very, very popular. So here are some examples. All frogs are reptiles, all reptiles are animals. So we can infer that all frogs are animals. So notice that this is the sort of stuff that would go down up in ontology. If we have an ontology of the animal kingdom, then we so like usually it's written or drawn as a graph, we might infer this, and that all frogs are animals. All sagatricians are multinomens, and all sagatricians are achems. So can we infer that all multronems are achems or not? So notice that the meaning of these words is not important. What is important in order to determine the syntax and semantics is the form of the sentences. And that's kind of like really handy for us, right? Because we know that computers do not understand the meaning. They simply operate on form. So that's kind of really helpful. We can have more than two premises, all x are y, all y are z, all w are x. So we should be able to infer that all w are a. So let's give the syntax of all. Based on the prior examples, we know that we have nouns, things like frogs, sagatricians, x, y, and z. Yeah, I know that typically in CS, x, y, and z are variables, but we just sort of treat them as nouns at this point in time. So notice that unlike the all universal quantifier that I've seen before, where we do specify a variable, over here we do not do that. We simply capture what is being said over here, all frogs are reptiles. So we don't have for all x, if frog x, then reptile x. We'll just have a shorthand for that if you wish. So as such, though, we do not have to use a more complex syntax where we sort of like introduce variables. We just sort of like use nouns. And we have sentences such as all x are y, all frogs are sagatricians. So notice that in our system, the sentences follow the same pattern. All, some noun, are, some noun. And are is the predicate. But again, we don't distinguish between different kind of predicates because our system only has one. That's okay. So we're going to leave out a lot of stuff, but for the purpose of understanding what does a syntax, what does a semantics bias, this is sufficient. So a term that we need to know about is a well-formed formula. So I already mentioned that the well-formed formula of all is P, the set of nouns, and then a recipe on forming sentences. So given elements P and Q of P, we can form a sentence of the form all P are Q. And these are all the well-formed formulae in our system. So now, and this is so the important part, is semantics. So a lot of times in AI, people gloss over the semantics or leave it out. So semantics is where, at the very least, humans attribute something to the symbols being used by our AI system. But a logician would give a semantics for any sort of like a logical system so that they can understand that the system is sound and complete. Two things that we will not get into in this course, but something that you should understand at some point in time. You really want to take a course on mathematical logic. A key concept in semantics, or two key concepts in semantics, are that of a model and an interpretation. So a model M, notice that the slightly different way of writing is a set M of items in our domain. So here are some examples. The set of all students in our class, or the set of all ancient Greek philosophers, or the intersection of those two sets, which presumably is empty, or the union of those two sets, which is not empty. So, lots of combinations here, but so simple examples is the set of all students. So that is the set M. So for each noun, then we have an interpretation. And the interpretation is a set of items from the specified domain that's assigned to that noun. So technically we're writing that the interpretation of P is a set, and that is a subset of M. It can be empty, it can be the entire set, it can be sort of particular things of subsets of that set M. So that's the interpretation of a noun. Now, we now say that a model M satisfies a sentence if the sentence is true in M. And we'll see some examples of what we mean by that here in a moment. So technically what we write is that the model supports a particular sentence, all P are Q. In other words, it is true in this model. So how do we know whether something is true in a model? Let's go to something that we all know about sets. So here is a domain. The domain consists of the numbers 1 to 8, M. So that's our set, and that's the orange rectangle over here. Okay, so going back to this one over here, we need to have a set M of items. And our items are the numbers 1 to 8. Now, we are now going to give an interpretation of the noun A. Okay, so that's what we're doing over here, an interpretation of A. And these are certain subsets. So it turns out that A is the black oval over here. So it consists of the items 1, 2, 3, 4, 5, and 6. The blue oval is consisting of is a subset 1 and 4, and the red oval is a subset 2 and 4. And I'll notice that some things can be parts of. Let me back up. Some nouns have more than one item from our domain in them. So let's look at A, X, and Y. So the interpretations of A, X, and Y all contain 4. That's fine. There can be duplication. Notice 4 is actually at the intersection of blue and red. So it's the only thing that is both blue and red. Notice that 1 is blue and black. Okay? 2 is red and black. And of course, orange. So that's sort of like the lay of the land. So now we have given our model. And now we want to understand whether some sentences are being satisfied by the model. So again, we have given an interpretation. We have specified what the nouns are, and the nouns are these subsets over here. So now we want to understand whether some sentences are true. In other words, or the example that we're going to look at first is the model supporting this sentence, all x are A? In other words, is the sentence all x are A true in our model? Well, let's have a look at that. What are the A? The A are everything in the black oval. And what are the X? Everything in the blue oval. So notice that the blue oval is properly contained in X. So yes, this sentence is true. All X are A. So what we can write is, yeah, so we write this one here. So let's look at another sentence. Is it true that all A are X? So again, A is the black oval and X is the blue oval. So the question is the black oval so like properly contained in the blue oval? No, of course it's not. Now notice that that's technically not the right question to ask, because if we were not to have 3, 2, 6, and 5, then yes, since 1 and 4 are part of the black oval and they're also part of the blue oval, all A would be X. But that's not the case. So how do we show that something is not the case, that this one is not being supported by the model? Well, we'll find a counterexample. So 3 is a great counterexample. It's an A, but it's not an X, right? It's a black oval, but not in the blue oval. So that's how we will give this semantics here. That if we find a counterexample, then we know the model doesn't support it. And how do we know that the model supports something? Well, if a subset is properly contained in another one, or if it is not contained, then all the elements that are in the outer set but not in the inner set are empty. There are no other elements. All right, so let's have a look at some more examples. Is it true that all y are x? So let's see, y is red and x is blue. No, we have 4 that is part of the blue oval, but not 2. So there's a counterexample. So no, that sentence is not true. All y are A. So 2, 4 is the red oval, and we have the black oval. Yes, okay. The red oval has 2 and 4. They're all 2 and 4 also part of the black oval. So yes, that is supported by our model. All A are A. Yes, that is also supported by our model, because the black oval is the same as the black oval. It's properly contained in itself. So here's what we're going to get then. All y are A is true, all A are true, and all y are X is not true. Okay? So there you have it, a very brief example of what a model helps us do. It helps us it helps us determine whether something is true. All right, that's it. I'll see you later. Bye.